In this video, we'll look at situations where one or both variables in our regression is an indicator variable. So I have a regression here of earnings in dollars on an indicator of whether the person has a college degree. So when we say indicator, of course, you're familiar with this terminology. We're talking about a 0-1 variable, what in another context we would call a Bernoulli random variable. This might also be called a binary variable. All right, so just takes on those two values indicating whether the person has a college degree. This is estimate of this model using data from the NLSY 79 or 97 that you've seen. Okay, the intercept is about 42,000, and the slope, the coefficient on college, is $24,000. Okay, the scatter plot here would look a little unusual, right? Because remember, the college variable can only take on these two values, and so all your data points would line up at college equals 0 or college equals 1. And then, of course, across people within those educational categories, there are different amounts of earnings. Okay, so we might say the intercept is somewhere in the middle here. That's our beta 0 hat. And then there's only two fitted values that are possible here. So when college is equal to 0, just strike this out, and you get this is the predicted value for the non-college group. Okay, that's the intercept. And then when college is equal to 1, you add up the intercept and the coefficient on college there, and you get the predicted value for the college group. Maybe it's around here. So this is the other fitted value that's possible, beta 0 hat plus beta 1 hat. All right, and we would interpret this as, how much higher predicted earnings are for people with a college degree compared to without. Okay. We can actually go a little bit further than this, though. This is an example of what's called a saturated model. And a saturated model, it gets more complicated when we get to multiple regression, but for now, it's pretty easy. The idea of a saturated model is there are as many parameters in the model as there are possible combinations of the explanatory variables. Here, there's only one explanatory variable because it's a simple regression, and that variable is binary. There's only two possible values of the college variable. And there are two parameters in the underlying model here, beta 0 and beta 1. So this is a saturated model. In fact, any simple regression model where the x variable is a binary variable is a saturated model. What's special about this type of model? Well, it has this property. The fitted values, after we estimate this with OLS, are equal to sample means of the dependent variable for the corresponding x values. So here, what that means is that when we see the intercept estimate is 41,998, we are saying that literally the sample mean of earnings for the non-college individuals used in this regression is that number, 41,998. And for the college group, the fitted value is just sum these two values together, and you get $65,601. That is a fitted value. Yes, it's this value right here, but it is also the average earnings for those data points. Okay, regressions in general don't always have this property, right? You have data points, you're fitting a line through it. There's no promise that the height of that line corresponds to the average value of y for every single different value of x that you could run along that line. But when the regression model is saturated, you do have this property where fitted values are equal to the sample means of y, and that's the case here. Okay, so that's one example of a regression involving an indicator variable where that indicator is on the right-hand side. Now, what if the left-hand side was also an indicator or also a binary variable? So here we're running back to the very first example you saw on these slides of intergenerational persistence of education. So remember, we had data on mother-daughter pairs. The outcome was the daughter's education, and the explanatory variable was the mom's education. I'm using the same sample here for this slide, but instead of years of education being how the variables are measured, we're just using an indicator of whether each person has a college degree. So this is an indicator of the daughter having a college degree, and this is an indicator of the mom having a college degree in that mother-daughter pair. All right. So how should we interpret these estimates? This is an example of a saturated model. Okay. So when we find the fitted values here, they correspond to sample shares of the daughters who have a college degree, depending on the two categories of like the mom's degree variable. Okay, so there's two possible values, of course, of whether the mom has a college degree. If we plug in 0 for that x variable, we will see all that's left is the intercept. And that's telling us that 29.5% of the daughters have a college degree, when the mom does not have a college degree. Okay, so plug in the 0 here. This, in this case of a saturated model, this is actually the share of the daughters in the sample whose moms don't have a college degree, the share of those daughters that do have a college degree. Okay, now if we plug in mom college equals 1, then we form the fitted value, of course, as 0.295 plus coefficient on mom college, 0.472. We get a much higher share, and this is also interpreted as not just the predicted share, who would have a college degree when the mom has a college degree, but the actual share in the sample of daughters who have a college degree among those whose mom has a college degree. Okay, so how would we interpret, if we just focused on this number right here, how would we interpret that? For that, we need the concept of a percentage point, okay? And you can see the definition here, a difference of 0.01 in a proportion or probability. So, for example, if you were looking at like state level data, okay, and let's say that college attainment rates were 30% or 0.3 as a proportion in South Carolina and 36%, 0.36 in North Carolina, we would state that that difference is 6 percentage points. And the reason we do that is because it would also be correct and true to say the difference between these two values is 6 on a base of, let's say, 30, if we were using the lower number as sort of the relative point. And we could say that that's a 1/5 or 20% difference. So we use percent to make that sort of relative statement, which means if we're talking about an absolute difference between two percentages or proportions, we need to reach for this idea of a percentage point. Okay, so I would say the difference between the two values we found here is not 47.2%. It is 47.2 percentage points. All right, so that gives you, a little bit of an intro to regressions with indicator variables.